First off, I would like to thank Pinaki and Arnav for inviting me. It's nice to be back in Chennai after 24 years, and I'm enjoying all the glorious comfort food per unit time as humanly possible. So it's after lunch. I know you all must be feeling sleepy. So I decided no glasses, no active matter, no resetting. It's going to be a bunch of movies. But what kind of movies? We all go around in circles. Okay. So simple kind of movies. But either you will come out hallucinating after, yeah, either you will come out hallucinating or hypnotized. Okay. So this work is just fresh off the lab. It's still not written up, and I'm still trying to think of the best way to present it. So this is the first time I'm presenting these results. So this is one way of presenting it. But if you have any feedback, I would be very interested. Uh, I would like to start off by explaining what the experiment was. It's a very simple experiment. Think of a tank of water, and we are exciting waves on one end, and we have a vortex, and it's an experiment that tries to study the scattering of these waves of this vortex. But it has connections to the famous Aharonov Bohm effect we study in quantum mechanics textbooks. And so I'm going to try to cast the results in that language. And there is a very rich history of these connections between hydrodynamics and electrodynamics that go all the way back to the founding fathers, to Maxwell, who used electrodynamics to advance his understanding of fluid dynamics, and Hermann von Helmholtz, who went the other way. He used his knowledge of hydrodynamics, sorry, he tried to improve his knowledge of hydrodynamics, especially vorticity, using electrodynamics. Okay. So this is also the first time in my career that theory, experiment, and numerics are matching. So I couldn't believe it when it happened. So we had to go and cross-check everything. So either we have done something trivial or we got very lucky. Okay, so before I proceed, let me tell you a bit about what we do. So my training was in turbulence, that graveyard of theories where you never get the satisfaction of having solved something. So you can understand why I'm excited about this working out. But slowly I'm getting into this topic on topological fluid dynamics. Another topic is, as I was quoting my good friend Shmuel Rubinstein earlier today, he said, when all else fails, there's always biology. So we do a bit of quantitative life sciences, and we are currently working on the predator-prey interactions between redback spiders and ants. And then something I started after I moved to Okinawa, which is fluctuations, applying statistical physics concepts to energy and sustainability to understand fluctuations in renewable energy sources. And then something I took up during my postdoc days at Los Alamos, which was granular media. I'm winding up that work on frictional granular jamming. I'm thinking of some tabletop experiments in triboelectrically charged granular matter, but it's a very difficult problem. And then there is an odd assortment of questions that don't get classified, which are just left aside. Okay. So the dramatis personae are, Jonas Roning is a postdoc with me at OIST. He did the theory and numerics for the work I will discuss. Aditya Singh is a PhD student. He did the experiments. Andres Concha is a close friend of mine. We both were postdocs at Harvard, and that is when, about 10 or 11 years ago, was when we first started cooking up this problem. But what I'm discussing today is not the problem we cooked up. So the story is non-linear. So he contributed to both theory and experiment, and Luisa Angeluta Bauer is a collaborator from University of Oslo. She contributed to theory and numerics, and I was settled between experiments and numerics. So it was a division of labor. So let me, for the benefit of students, I'm going to give you show you this YouTube video about how the B field works in a magnetic field works in a solenoid.
If the solenoid carries a current, it produces a magnetic field that is parallel to the axis and close to constant inside the solenoid. The magnitude of the magnetic field is proportional to the current and to the number of turns of the solenoid, divided by its length. Outside the solenoid, the magnetic field is very small, as can be seen from the small magnitude of the readings, which is represented by the wide spacing of field lines in the diagram.
Okay, so that's the conceptual background you need to understand how a solenoid works. The last bit that the speaker mentioned, that there's a slight leakage of the magnetic field outside of the solenoid, is relevant in part to what I'm about to explain. So when we study the forces exerted on a charge in classical electrodynamics, we basically work with this equation for the Lorentz force from 1895. And in this classical picture, the fields are the primary drivers of force. They take the center stage. Okay. Potentials are always considered a mathematical convenience. They lack any physical significance because, as we all know, potential can be defined up to within an additive constant, right? But this view changes when we go from the classical to the quantum realm, where particles can also behave like waves, and waves, as we know, can have a phase as well. Therefore, one must consider not just the deflection of particles by these external forces, but also the change in their phases. Okay? But the E and B fields are not the primary physical quantities to study phase change, rather it's the scalar and vector potentials from which they are derived. So this became the conundrum, so to speak, when Aharonov and Bohm and few years prior to them, Sida and Ehrenberg proposed this thought experiment where they said that you can have measurable consequences of the vector potential, the magnetic vector potential. I'll come to that in the next slide. So phase is an argument of a complex number of unit modulus associated with the cyclic evolution of a physical system, specifically of a physical parameter that leads to a net change in the phase that depends upon the path geometry that the particle takes. So if the potential changes the system topology, this induces phase shifts which we call geometric phases. The most elementary form we study in high school laboratories is the Newton's rings. That is the most elementary form of a geometric phase we study in physics labs. Now, when we move from the classical to the quantum picture, let's imagine we have a charged particle under external influence going around a solenoid. We have the kinetic energy operator and the time-dependent Schrodinger equation. When we evolve this equation on the wave function psi, it picks up this phase which has, so the wave function has no contribution coming from the vector potential A, but the phase does pick up a contribution from the vector potential. Okay, and this is basically coming from phi sub b. So basically this vector potential is encapsulating the total magnetic flux enclosed within that cycle. So the Aharonov Bohm effect, when we study it, comes about through this picture. So if you imagine that you have if you imagine you have a bunch of electron beams going past a solenoid here, where the magnetic field is zero outside of the solenoid, but the vector potential is not, then the path taken by these electron beams is going to give you an interference fringes. Of course, if the solenoid is shut off and the vector potential is zero and the magnetic field is zero, even then you will get interference fringes. But when you turn on the magnetic field, which is zero outside of the solenoid, but the vector potential is not, there is a quantized phase shift in the interference fringes. And that quantized phase shift is captured by this quantity delta phi, which is q over h bar c times the enclosed magnetic flux. And this can be traced to the path difference with where you have a topological pickup here. Okay. Now, this picture differs from electromagnetism because there only the electric and magnetic fields have observable effects, right? Now, in 1980, Michael Berry and co-workers did a nice experiment, literally in a bathtub. So Michael Berry filled up a bathtub with water and then pulled the plug out. So you have a vortex that is draining the bathtub, and he set up surface waves, the traveling waves that are approaching the vortex. And he showed that when the surface waves approach the vortex, they tend to accelerate a little bit. So you can see this in, oh, I'm hitting the wrong buttons here. Okay, yeah. So you can think of the electron beams or the wave function of the electron beams as the surface waves that are striking the vortex, and the vortex itself is like the solenoid. And you can notice that when the wavefronts strike the vortex, they develop a dislocation. And this can be explained through a dislocation parameter, alpha, which goes as q over h times phi sub b in the quantum case, and it has a classical analog in which shows up. Why isn't it coming up? Okay. So in the fluid analog of this quantum effect, you basically draw a mathematical correspondence where the vector potential is like the fluid velocity, and the curl of the velocity, which is the vorticity, is like the magnetic field, which is the curl of the vector potential. And you have the surface waves that are striking this vortex, and you have wavefronts that are now unobservable, and you can go between the quantum and the classical case. Here you can map the Schrodinger equation to what we call the shallow water wave equations in fluid dynamics. The math is simpler in the quantum case, which is where we did all the theoretical, sorry? Eta is the viscosity. So the math is easier to work out in the quantum case, but you get better intuition because you can see everything in the classical case. Okay, now that is what Berry had done, and there have been many nice works following up on Berry's beautiful experiment. What we decided to do was study it with standing waves. I'll tell you the truth, that is not what we originally decided to do. We also started with traveling waves, but we were having some difficulty with the wave maker. So I told Aditya, our student, why don't you, we have these acoustic transducers in the lab, why don't you just stick them to an acrylic plate, set them on the surface of water and excite waves and set up standing waves so that we can calibrate our experiment. But when he did that, he saw something and we tried to remove it, and then Jonas said, I see it in the simulations too. And that is where the story went off at a tangent, okay? So what happens is when you have standing waves, you can decompose them into two traveling waves coming in from opposite directions, okay? And these are linear equations. We simply add up the traveling wave solutions. But counterintuitively, the dislocations do not just simply cancel. Instead, you get what I like to refer to as the BMW propeller going around in circles. So what you see is basically a far field structure for this interference pattern, which leads to the nodal lines. Nodes, as we study in wave mechanics, is basically where the phase goes to zero, right? So you have the wave function for the traveling waves coming in from the right, going past this vortex, and then you see the dislocation over there, and you have the waves coming in from the left. The picture is just inverted, and if you add them both, you get this instead. You have standing waves, but you have these rotating lines with zero phase that run exactly in the opposite direction to which the vortex is going in. So if the vortex is circulating clockwise, the nodal lines go counterclockwise. And this comes about, you can show through some mathematics, is basically there is this phase term and then the rest of the wave function. In this phase term, you have these three terms. The first and the third term are time independent, but you have a time dependent term here with a negative sign. And that is what is causing the nodal lines to rotate in the opposite direction. So it's as simple as that. And then if you start changing this dislocation parameter that I mentioned, it determines the number of nodal lines you get. So when alpha equals 1, you expect to see two arms of the nodal line about the vortex, which is at the center. If you move slightly past 1.25, they split into two pairs, ever so slightly. And as you approach 2, you get two pairs of nodal lines. You go to 3, you get 3 pairs, so on and so forth. Okay? So to tell you about how we did the simulations, it's a very simple simulation that you can run on a laptop on Mathematica. So it's a standard wave equation with time derivative replaced by the material derivative. The velocity is said to be that of the Rankine vortex by Fiat. The Rankine vortex is basically a vortex with a solid core, okay, so that you have an irrotational vortex. The waves are produced by adding an oscillating source term, and we have periodic boundaries with a damping term like a damped harmonic oscillator, so that we can avoid recirculation of the waves. And then we do the time integration using the fourth order Runge-Kutta scheme and space using Fourier transforms. So as I said, this is a simple and minimalist numerical scheme. Run it on Mathematica on a laptop, nothing fancy. I'm not lazy, I'm just an effort minimalist. Okay? So now I'll come to the results. So on the top you see the traveling wave solution, and the bottom you see the standing wave solution. So the top one is what Michael Berry had worked out initially. So the traveling waves have dislocations in the phase over here, and I'm plotting both the amplitude and the phase for you. The nodal lines are acting as domain walls. You can see it sort of here. But in the standing wave case, you get these propellers, and you can capture them more clearly in the phase plot. Okay. Now these lines, as I said, move in the direction opposite to the flow, for the reason I showed you in the previous slide here, because there's a negative sign here. And now what you notice is this is a quantization that is happening, but it has nothing to do with quantum mechanics. This happens in both classical and quantum mechanics. But phase is not an observable in quantum mechanics. That was the original reason why Michael Berry did the bathtub experiment in the first place, because it can be observed in the classical analog. Right? But so phase is observable in the classical case, so that is why we are able to observe it here. And then we move from, so this is for alpha equals minus 1.5, but if we go to minus 1.1 and minus half, all the results are borne out. You see the splitting of the pairs, and then they become, so you can sort of make out here just about the horizontal line. It splits into two pairs and then goes back to a single pair. So basically the quantization is closest to the nearest integer of alpha. So now coming to the experiments. So this is a photo of the experiments. We have a tank about 1 meter in length and half a meter in width, and we fill it with water to about 20 centimeters in depth, and we drain, we have basically a drain at the bottom of the tank to generate a vortex that is basically draining the water using a water pump. So we can control the strength of the flow rate or the circulation as a result by controlling the power of the water pump. Through that, we can either have a tubeless or a vortex with a tube. In this case, all the experiments were for a tubeless vortex. And then these are the these two are the transducers on one side, though you see two more transducers on the other side. They are fixed to an acrylic plate, and these are piezo transducers, so they are connected to a function generator through an amplifier. So they are sending out acoustic waves. Now the acrylic plate acts like a speaker, so it gives you uniform and homogeneous, spatially homogeneous acoustic excitation. So it basically moves the acrylic plate up and down to generate the waves, and the standing waves are generated in between. Okay, and below this tank we have a light source, a diffuse light source with a Gaussian filter above over here, and you don't see it, but I can move this photo. That is the camera with which we do the imaging. So it is a bit of a it's a bit difficult to get Gaussian diffusers of that size. Those of you who do experiments, you will know that if you were to purchase a Gaussian diffuser of about 5 centimeters by 5 centimeters from Thor Labs, it will cost you about a few $100s. So we got this Gaussian diffuser by breaking apart one of these monitors. You get they are very high quality Gaussian diffusers and Fresnel lenses. So you hack your computer or your monitor, you get a lot of experimental parts. Now for to calculate the vorticity and the velocity field, we do it through particle imaging velocimetry. So you see a pipe here that's basically sending a laser beam down here, and we pass it through a cylindrical lens to to illuminate the surface, and we have tracer particles on it. And using that, we can track the tracer particles to pull out the vortex, the velocity field around the vortex, from which we can pull out the vorticity. And once we have that, we can then do the experiments after calibrations to look at the amplitude and the phase after post-processing of the images. And this is at alpha equals 0.68, so you don't see anything yet. This is actually a traveling wave experiment. But you come to alpha equals 0.5. Once the standing waves are set up, they're in the process of getting set up, you start seeing that propeller. and then you move to close to alpha equals 0.9, and you can see the propeller even more clearly. (1.1), you start seeing a figment of the pair splitting ever so slightly, just for a moment around the horizontal when the propeller crosses the horizontal. But once you reach 2.1, you can see two pairs of propellers. So I'll show you static images where it will be more clearer, hopefully, but you can sort of make out. So here we should have 3 pairs, but we couldn't do a good job. We are still working on this part to get it up to 3 pairs. But to give you a better idea, you see the wavefront dislocations here. This is at alpha equals 0.5, and that is the line at alpha equals 0.9. Once we get to 1.1, you get 2 pairs here, and at 1.9, the angle between those pairs has increased.
Can you just remind me what alpha was?
Sorry. Alpha is basically the dislocation parameter, which is the circulation divided by the group velocity. So we are coming up with a dimensionless parameter that is linking quantity coming from the vortex to the quantity coming from the waves.
And you can control that besides the waves, right?
Not control, but we can. So our controls are basically the frequency of the waves, and therefore the group velocity to some extent, and we can control the flow rate of the pump, through which we can control the vorticity and therefore the circulation. But we can't say I want alpha equals 2 and tune them, but we can vary these two and see, okay, how close do we get to alpha. So to summarize, what I have described is basically a classical analog of the Aharonov Bohm effect, which is well known in the hydrodynamic context. And we have studied the same using standing waves instead of traveling waves, and that gives rise to this cyclic interference pattern with rotating nodal lines. These nodal lines arise in quantized pairs proportional to the nearest integral value of the dislocation parameter, and they always rotate with a sense opposite to that of the vortex or the solenoid if we are working in the quantum mechanical case. And they should arise in both the quantum and the classical cases, because we solved the problem theoretically in the quantum case, but we measured it in the classical case, right? Oops. The standard quantum Aharonov Bohm phase shift is actually routinely used these days in certain interferometric measurements. So, we know that the rotating nodal lines are more sensitive than the standard quantum Aharonov traveling wave case. So we are currently exploring if there are any potential applications of this more sensitive technique. So this is the summary of what I have described. I would like to share a bit about where do we want to head from here. Usually I'm known to do standalone experiments. I do one and then go off like a bunny rabbit and jump into a totally different field. So where we want to go next is look at classical analogs of other quantum geometric phases. So there is actually a family of these. The Aharonov-Kasher effect, which is the dual of the Aharonov Bohm effect. In the Aharonov Bohm effect, you have electron waves striking a solenoid. In the Aharonov-Kasher effect, you have a magnetic dipole in an electric field. Then the Aharonov-Anandan effect, which is considered the superset. So the Aharonov Bohm and the Aharonov-Kasher effect are special cases of the Aharonov-Anandan effect. And Anandan, it turns out, he's my academic sibling. He got a PhD from the University of Pittsburgh, but before I was born. And then there is the Aharonov-Carney effect, which considers the principle of equivalence between real and inertial forces, the potentials of real and inertial forces and their consequences. And then we want to go into collective Aharonov Bohm phases. So this would be trying to create a vortex crystal. So in superconductivity, when you have a supercurrent striking the Abrikosov lattice of magnetic flux tubes, the solution we know is what we call the Hofstadter butterfly, right? So if we did create a vortex lattice in a tank and we sent in these waves, what do we expect to see? I mean, we are not going to see the Hofstadter lattice, but what are we going to see? And then look at some exotic cases like hydrodynamic lensing, cloaking metamaterials. So here is an example where Jonas has created a Fresnel lens configuration for the vortices, and he's looking at how the interference fringes get focused as you change the curvature and the number of vortices in their sense. So that is where we are right now. They're very early days. So I'll stop there. Thank you, and take any questions, rotten eggs, tomatoes, etc. Thank you.
I think the classical analog AB effect is only valid in viscosity limit.
Yes.
So that if the viscosity exists, what happen only to this dispersion? Dispersion suppress the such effect, or
No, dissipation actually aids us. Yes, because it allows us to design experiments with waves in the linear regime. All these, the nonlinear waves is an exotic topic in itself in hydrodynamics, but we are working with the simplest form of linear waves. I mean, another reason why theory, experiment, and numerics work is everything is linear here.
okay.
But it is still out of equilibrium, so it is part of the topic of this conference.
Unroot is better.
Sorry?
How does it get unroot?
So in this vortex, if we draw the tube, if we increase the flow rate, the point that a vortex tube is created. So you're basically changing the topology physically in physical space from a genus 0 to a genus 1 object. At that time, every time a droplet is pinched off due to the Rayleigh-Plateau instability in the fluid, there are waves that that are radiated, spherical waves that are radiated outwards. So technically it should not be possible because the fluid is accelerating so fast, the wave should not be going out. They shouldn't be getting out of the vortex. So we don't yet understand. It may not be related in any way to Unruh radiation, but it is one possibility.
Like, do you get like your sine waves when you do it, or like,
Yeah.
do you have to? You don't have to like.
We just set up simple sine wave on a function generator at 4 hertz, 5 hertz, 10 hertz, 20 hertz, connect it to an amplifier and connect it to the piezo transducer. It's simple.
Hi, when you do this PIV analysis, if I understand right, like you are having a 2D sheet on which you are looking at. So now your system is intrinsically 3D. So if you look at different heights, do you see that how does your result scale with the height of the channel?
Okay, so we are not doing PIV on the waves. So we have to do PIV on the vortex because we have to pull out the circulation, the vorticity and the circulation. But for the waves, we just can get away with caustics through by looking at the caustics of the wave fronts. So we don't need to do particle imaging velocimetry there.